Thousands of disorganized puzzle pieces swirl into a tight sphere. It looks unified from a distance, but the internal structure is pure chaos. In software engineering, we face a similar paradox. Simply grouping code elements together into a single module does not automatically create a well-structured design. The foundational axiom of software architecture states that good design requires two specific conditions: high cohesion and low coupling. Cohesion measures how closely related the tasks within a module are. But that raises an immediate question. If two different modules are cohesive, are they equally good? The answer is definitively no. You can bundle functions into a single file, compile them without errors, and still produce a structural disaster. To evaluate the actual quality of an architecture, software engineering strictly classifies cohesion into a qualitative hierarchy. This diagram illustrates that framework. There are exactly 7 distinct types of cohesion, occupying tiers that scale from the worst possible design at the fractured bottom layer up to the solid top. Locating where a module sits on this 7-tier spectrum identifies the boundary between code that breaks during maintenance and code that scales effortlessly. At the absolute bottom of the hierarchy sits coincidental cohesion. This is the weakest and most dangerous form of software design. The rule here is simple. There is no rule. Functions are grouped together in a module purely by accident, with zero logical relationship to one another. Think of a physical junk drawer in your kitchen. You might open it to find pens, a pair of socks, and a mobile phone charger. They are occupying the same space, but they serve completely different purposes. Look at the pseudocode typing out in this dark mode editor. We have a single module attempting to print invoices, log in users, calculate salaries, delete databases, and play music. These tasks are entirely unrelated. When a module is built this way, the code becomes nearly impossible to read. It is incredibly difficult to test, and because it handles so many random tasks, you can never reuse it in another part of the system. Stepping one tier up the hierarchy brings us to logical cohesion. At this level, functions are grouped because they perform the same general category of work. However, they remain distinct, isolated tasks. Imagine a customer service employee. Their category of work is communication. They handle phone calls, emails, and chat messages, but they can only process one of those channels at any given time. This flowchart for an input module demonstrates the concept in code. The module is categorized around reading inputs, but when you trigger a control flag, only the mouse path executes, leaving the keyboard and scanner paths completely inactive. Logical cohesion organizes elements by category, which is an improvement over pure coincidence. But because only one specific function executes at a time, the module still lacks a unified, simultaneous purpose. Moving up to the 3rd tier, we reach temporal cohesion. Here, time becomes the primary organizing factor. Under the temporal rule, functions are grouped exclusively because they must execute simultaneously during a specific phase of the program's lifecycle. Consider a morning routine. Brushing your teeth and eating breakfast are very different tasks, yet you group them together as a block of activities simply because they all occur in the morning. This timeline models a system startup module. Memory initialization, configuration loading, opening log files, and network booting all trigger at the exact same moment on the timeline. They perform different jobs, but they share an execution window. The 4th tier introduces strict order. This is procedural cohesion. Instead of simultaneous timing, the procedural rule dictates that functions are grouped because they must follow a mandatory sequence of execution. Step 1 must finish before Step 2 begins. If you withdraw cash from an ATM, you have to follow a fixed procedure. You insert the card, enter the PIN, and then select the amount. The machine dictates the exact order. You can see this in a strictly vertical flowchart for a logging process. The system must read the username first. Only then does it proceed to read the password, validate the user, and finally display the result. Procedural organization guarantees a reliable order of operations. But there is a critical limitation here. These sequential functions do not necessarily share or process the exact same underlying data. Time and sequence give a module necessary structural order, but for an architecture to achieve true cohesion, the functions need a deeper, data-level connection. That data-level connection begins at the fifth tier, communicational cohesion. This is the official entry point to high-quality software design. The communicational rule is clear. Multiple operations are housed together because they operate on, or produce, the exact same core data element. In a student database system, the function that calculates a final percentage and the function that prints a report card rely entirely on one single student's record to do their jobs. This diagram maps the architecture of a customer record module. You have three separate functions: updating an address, displaying details, and printing an invoice, and all three draw from one central unified data object. Anchoring functions to shared data dramatically improves system coordination. If the data structure changes, developers know exactly which module to check, making maintenance straightforward. At the second highest tier, we find sequential cohesion. The sequential rule takes data sharing a step further. The distinct output of one function becomes the absolute mandatory input for the next function in the chain. Think of making tea. You boil water, which is then used to steep the tea leaves. The steeped tea is then poured to mix with milk. Each progressive step physically relies on the product generated by the step before it. Here, a horizontal pipeline demonstrates this chain in code. The first node reads raw data and outputs a block. That specific block slides directly into the next node to be processed, which then outputs a refined block that acts as the input to generate the final report. Creating an unbreakable chain of data flow represents excellent natural design, but it remains one step below the most refined level of the hierarchy. Tier 7 is functional cohesion. This is the highest, most optimized type of cohesion in software engineering. Its rule is uncompromising. Every single element inside the module contributes to one and only one well-defined task. The addition button on a physical calculator is the perfect analogy. You press it and it performs addition. It does absolutely nothing else. Inside this perfectly optimized login module, you can see three specific functions. The system reads the credentials, authenticates the user, and creates a session. Every single line of code exists exclusively to achieve one solitary goal: logging the user in. This pinnacle tier achieves what modern architecture calls the single responsibility principle. The code is isolated so precisely that modifying the login process will never accidentally cascade and break the payment system. Software engineering examinations frequently ask students to arrange these 7 types in exact order from worst to best. To memorize the sequence, use this phrase: crazy lions take powerful cats seriously first. The first letters give you the strict hierarchy: coincidental, logical, temporal, procedural, communicational, sequential, and functional. As you move down this list, the internal relationships grow stronger, and the overall quality of the module improves. To see why this matters, consider the stakes of